look at an introduction to logistic regression, I find logistic regression to sort of be the catch-all, and sort of fitting that it's last because of the parameters that you can use to use logistic regression. And you'll see that as we get into the details of it, that it really is a little less complicated because of the assumptions and limitations that are associated with it than some of our other statistical procedures. The purpose is for the classification of individuals into groups. And that's what we've seen that we did last week, but now we're going to do it in a different fashion using different types of data that we've collected. One of the unique things about logistic regression, unlike the other statistical methods that we've been looking at, is that the independent variables, or the predictor variables, have very few assumptions associated with them. The ideas of normality, linearity, and homoscedasticity are sort of not as important for logistic regression as it has been with some of the others. The dependent variable are the criterion variable. They are going to be in two categorical groups that are not continuous or quantitative. You can have more than two, but this is going to be the focus of our chapter, where we're going to do a dichotomous dependent variable, where we have one of two groups that you can be selected into. The procedure is that you do a regression equation that accurately predicts the probability of whether an individual will fit into one category or the other. Now, the predictors, or the independent variables, do not need to be normally distributed, linearly related, and equal variance. Again, those are the four things: normality, linearity, and homoscedasticity. The results cannot be negative because the kind of math that is done, you're going to get scores between 0 and 1, and the independent variables can be continuous, discrete, and dichotomous. So your scaled data, which is ordinal and ratio, can be used as a part of your independent variables, and the dependent variables can be nonlinear with one or more of the independent variables. So you have a lot of variety and leeway in the kind of variables that you're going to be using in logistic regression. Now, in the assumptions and limitations, there are some, but they have to do with the size and how you're using the logistic regression. First of all, there are the ratio of the cases to the variables. And if you have fewer cases with a lot of variables, you're going to get difficulty in your logistic regression. So you want to reduce the variables to increase the rate, or the ratio, of the cases to the variables. Then we'll be using a chi-square chart, a goodness of fit, and so we want to remember our details about chi-square and the frequencies. Every cell has to have at least one or more characters in it, and no more than 20% of the cells can have 5 or fewer numbers in it. So if we find that in our chi-square cell setup that we have some of those violations, then again we need to reduce the number of variables so we can increase the cell count for each part of the chi-square. And then we have high correlation among the independent variables, where the same two variables are creating the same kind of effect. We again go back to when we've had that in the past, and that's where we reduce the number of variables and we decide which of the variables are redundant, and those we take out of the equations so that we have a better situation and we know which variables are actually doing the impacting on our prediction. Then we're also sensitive to extreme outliers, and here we're going to use the same techniques that we've used in the past. The primary one be looking at the Mollinovus distance and looking at those that are beyond the chi-square values that are significant for Mollinovus distance and eliminating them from the equation. So those are the four assumptions that we need to look at as we work through what we're doing with the logistic regression. The interpretation of the results in logistic regression actually take 3 steps, and these are defined in 2 different places in your textbook. I've put them in one to cover the ideas so that we can see it all together. You also are going to have to run SPSS twice. It's very simple because this is a pretty straightforward statistic, and you're only going to check a difference in one place, which we will show you in the SPSS lecture. But you want to make sure you do this so that you will get the charts that you need to make the interpretations of your results. The first step, and you're going to use the after steps selection to produce this chart in the SPSS run. And here you're going to get the statistics for the overall model fit. And these are going to be your chi-square of goodness of fit, and this is the actual values that you had in your data that are compared with the predicted variables. Remember, in chi-square, we did the observed with the expected. Here we have actual, which were the observed, and predicted, which are expected. And it's the difference between the constant-only model and the model that is generated. And we're looking for significance of the model. Now, a large sample size increases the likelihood of finding significance when a poor fitting model is produced. And so we're going to have to be careful as we interpret our findings with this in looking at our sample size. And again, remember that no fewer than 20% of the cells can be less than 5, and none of them can be less than 1. Continuing on in that same idea, then we get the statistics for the overall model fit. And here we're going to get the -2 log likelihood. And a perfect model would be 0. So the lower this value is, the better the model fit is for making the accurate presentations. And this is the sum of probabilities associated with the predicted and actual outcomes for each case. You also have your Cox and Snell R-square and your Nagel-Kirk R-square. And these are going to be two values that are two different approaches to the amount of variance in the dependent variable accounted for by the model. We come into our second SPSS run, and here we're going to use the step selection method, and you'll see where this comes when we look at SPSS. And this is going to produce a different set of outlooks, and it's going to give us a classification table. And here we're looking for how the individuals groups have been classified, and we're looking for the percentage of accuracy in the classification. And this is one number that we will look for in this printout. Now, step 3, we get another chart that has several different ideas into it, and that's what we need to understand what these mean. First, you're going to get your beta, which we've looked at before when we've used regression, and it represents the effect of the individual or predictor variables on the dependent variable or criterion variable. We'll get the standard error of the beta, and then we get a new statistic, the Wald statistic, and this measure of the significance for beta, and each of the variables contributes to the model. And you want to look at that and see what that number is, then the normal degrees of freedom, which we understand, and then we look at the level of significance of the Wald statistic. And what we're looking for here are those variables that have a probability that is statistically significant. Your textbook talks about an R value that's in this chart, and that is now not shown in SPSS. I don't know if it was an older model that they were using, and actually I've looked in other textbooks and I cannot find a discussion of this R value. So this may be a mistake in the textbook, or like I said, it may be something that was included in older models of SPSS that has now been decided it's no longer needed. But this is only discussed here in this textbook, and so just don't ignore that, because we're not going to have anything that we can report on because it's not produced by SPSS. And then finally we get another new variable, and that's the exponent B, or the phi, and this is the odds ratio. And this is the odds of this ratio happening in the percentage of classification. If we increase the odds of being classified, then we have a number greater than 1. So if this number you see is greater than 1, that means the odds of being classified correctly are going up. If it decreases the odds, when we're not having as good a chance of having the odds being predicted, then this number will be less than 1. So the closer this number is to 1, the less we have a chance of making the prediction. The further away from 1 this is, the better our odds are that we're making a good prediction. And all of this will come clear as we look at our SPSS printouts, which again will take us through these 3 steps with the 2 runnings of SPSS.